All right, hi stats. This is notes for 6.2, the second part. So make sure that you've watched that first part about how to use your graphing calculator and how to use a z-table to find normal distribution probabilities, all right? So we're going to go back to talking about these random variables, and we want to talk about as well, do you remember when we were looking at distributions and we would just say whether they were skewed or not, and they had all of those types of things going on? And we talked about that if we brought in a number and we added to it, that the entire graph would just shift one way or another. So we're going to be using that concept today. So we want to review with you that when you're adding or subtracting a constant, like adding 7 to everything or anything else, the entire shape of the original distribution and the spread of the distribution doesn't change. It's just going to shift either up or down by whatever that constant is. Okay, so let's say that I had an average of 10. And let's say we're not even going to worry about what kind of distribution is, whether it's skewed one way or normal or anything else. We just have that kind of we have a distribution. Its mean happens to be 10, and then we ask you to add 7 to every value that created that distribution, right? So if there was a bar that was so amount high, all of those numbers are now moved over plus 7. So that means that every number in the distribution would just shift 7 to the right. And now my new mean would be 17, right? Okay, my minimum amount would have gone up by 7 as well. My maximum would have gone up by 7 as well, but my range would have stayed the same because it's the distance between high and low. And my standard deviation would have stayed the same because that's a spread as well. Okay, so it doesn't matter whether we move a distribution up or down, right? You just move the entire thing. All right, but if we're going to be multiplying, okay, if we're going to be multiplying instead, or dividing by a constant, the shape doesn't change, but the mean and the spread will stretch or shrink by the amount of the constant. So again, here, if we had x bar equals 10, and I asked you to double all of the values, which means times 2, right? If I asked you to double all the original values, every value, then what would happen to the mean? So the mean would double. So our new mean would just be 20. Okay, but the standard deviation would change. So now we have it more spread out, right? Because the lowest multiplied by 2 does not move as much as a really large number multiplied by 2. So essentially, I'm going to draw this as if it's a normal curve, but it really doesn't really matter. If I started out here as 10, and let's say the standard deviation was 2, and I multiplied everything by 2, my new mean is going to be a 20, but it's now going to be much more spread out. And my standard deviation is now going to be a 4, right? So it's going to be more spread out, okay? So in this case, again, math to the mean stuff, to whatever the middle is. So whether it's add, subtract, multiply, or divide, you just do the math to the mean. The thing that you need to be careful of is what happens to the spread. So if you're adding or subtracting, the spread does not change, but if you're multiplying or dividing, the spread will either stretch or shrink, depending on whether you're making it bigger or smaller. Okay, what would happen to the range? If I'm adding or subtracting, the range stays exactly the same. But if I'm multiplying whatever that high number was before, it's now 2 times higher, and the low number is 2 times. So it moved up a little, but not nearly as much as the larger one did. So my range would get bigger as well. All right, so now we're going to go into the random variables. Remember, these capital letters just represent things that could change many, many, many times. So if there's, the number of shoes in different houses, right, if that value is going to change depending on what house I'm in, all right? So if we're dealing with 2 random variables, an x and a y, and they want the mean of the sum of those, no big deal. You just go ahead and you take the sum of those 2 separate means and add them together. Not a big deal. Okay, so we just do the math because it's the mean. Okay, so means will always follow that rules. Whenever you're trying to figure out something about means, just do the math. If they say to add it, add it. If they say to subtract it, right? But the standard deviation, that's the one we really have to be careful to. And in random variables, we are assuming they're independent. We're not assuming that if I go and check the shoes in one house, it's going to have any change using somebody else's house. Okay, so we are assuming that they're independent. So if remember that the relationship between standard deviation and variation or variance, remember, is a square or square root. So if I have a standard deviation and I'm trying to get to variance, I square it. And if I have variance and I'm trying to get to standard deviation, you take the square root of it. So usually we're trying to find standard deviation. So we're usually using this formula here. All right. So the variance, remember variance is just the square of standard deviation, right? So if I'm trying to add those two random variables together, x and y, then you're going to go up to variance and add those two together. So not a big deal. You just have to make sure you do it at the variance level. So if I want you to add standard deviation together, look at what's on the other side of that equals. It's not the standard deviations being added together. It's the variances being added together, and then we square root the whole thing to come back down to standard deviation, okay? So I'm going to write down here, don't add standard deviations together. Only variance gets added together. So anytime they talk about standard deviation with random variables, you're automatically going to go to variance to do any math to it at all. Now, again, we talked about this once before, I thought. Variance when we're doing x minus y, we're still going to do a plus y here because they are still looking at how much things have changed. And if these are two random variables that can change on their own, then when both of them move, I'm going to get twice as much spread as before. Okay, so the variance is going to add together. And I don't know that I said that exactly right, but that's a general idea. So if I'm trying to find the standard deviation of x minus y, I'm still adding the variances together because both of those random variables can vary on their own. So it's going to be different than just saying suddenly the variance is less because we're subtracting the two random variables. They're not. Each random variable varies on its own, and the more you put together, the more opportunities you have for the spread to get worse and worse. Okay, so even if they're asking you to do the subtraction of a random variable, if you're looking for standard deviation of that, you are still going to add. Okay, it is only add variances, never subtract. Never subtract. Okay. All right, and then it looks like I said the same thing down here. So recap, when adding or subtracting random variables, always add their variances for standard deviation calculations, right? Only add variances together, never subtract variances apart, all right? Okay, so let's go into some problems where we can actually practice some of the stuff. So we're gonna go and practice and find some average value. And again, we're gonna show you how to do this on your graphing calculator since we just used it in part 1. We may as well show you how to do this part in part 2 as well. Okay, so if we have a probability table, and in this one, I'm looking down at example 1, X is the number of family members in one town and Y is the number of family members in town B. So, you know, if we go and knock on somebody's door in town A, they are likely to have either one person in the house, 2, 3, 4, or 5. Simplified version, I'm sure there's some families that have more. And then if I go into town B, they're going to have 1, 2, 3, or 5, but at different percentage rates. Okay. So if I want to figure out what the average value is, we've already learned how to find average value, right? Our average value calculation looks something like this. So let's go do this one on our own. If I was going to try to find average value of this one, it would be expected value of X, right? That would be that mu sub X. And we would do 1 times its probability plus 2 times its probability, right? It's that weighted average from 6.1 plus 4 times 0.2 plus 5 times 0.3. Okay, and if I add those all up, I believe I get 292. That's a lot of just minor calculations. So if we want to do this in the calculator, we're going to use our lists first of all. Okay, so we're going to call this one list 1, and we're going to call the probability list 2. So the frequency that something happens is going to be list 2. Okay, so when we want to go and calculate it, it's really just going to be one variable stats because we're only talking about random variable X. So let me bring in our graphing calculator so we can do this together. All right, bringing it in. Okay, so under list 1, so I'm going to do stat, enter. Okay, I'm going to go up and clear all of these out by pressing clear. Going over to the next one, up at the top, hitting clear. Going over to the next one at the top, pressing clear. And this one at the top, actually I do want 1, 2, 3, 4, 5, so I'm just going to delete this one entry, okay? All right, so up here I'm going to write in all the probabilities. So the probability of having one person in the house was 0.07. Next one was 0.2, 0.5, 0.2, and 0.03. Okay. All right, so I've got them in the list. I'm going to go back to my main screen by pressing second quit. Okay, and I'm just going to go do one random variable. So that was stat. Then we go over to calculate. We press 1 for one variable stats. Okay, but remember, we actually put stuff into 2 different places. So the first thing, the main thing that I really care about is what are the number of people in the household? That's list 1. And before, I always told you don't worry about frequency. Here's where we use them, is in probability tables. So now I want to tell them, hey, that stuff in list 1, the 1, 2, 3, 4, 5 people, they have different probabilities. And to find those probabilities, go look in list 2 and match them up. And it will do that. It will match the first item in the first list to the probability in the second list and calculate it. So when I go and calculate it, there's my 2.92 that I calculated by hand, and also here is my standard deviation. So I also have the standard deviation, so I don't have to do that one the really long way. So this is 0.891. Okay, so I'm going to take that back over to our notes and write it in. Okay, so what is the expected value for this one? It is 2.92, and the standard deviation of X was 0.891, I think it was. Okay, all right, so then we're going to do the same thing again, and this time we're going to do this one as list 3 maybe and list 4 to find what the expected value is of Y. And so remember, all that expected value stuff is right here. Right? So I'm just going to go and recopy some of this. So the expected value of X is equal to 2.92. And now we're going to go and find the expected value of Y is equal to. So again, back to our calculator. We're going to go put those numbers into list 2. So back here, press stat, then enter. I'm just going to go over to the next one, and I'm going to use the exact same number. So I'm going to cheat here, and I'm going to tell it, hey, just go put in list 1 for me, and it's just going to recopy it. I'm just cheating. You can type them in. Okay, and then these probabilities are going to be 0.2, 0.3, 0.4, 0.08, and 0.02. Okay, so again, get out of this by pressing second quit. And we're going to run one variable stats again. So stat, move over to calculate, choose enter for one variable stats. And now I want list 3. So that's blue 3 and blue 4. And we go and calculate, and they're saying this expected value is 2.42 with a standard deviation of 0.961. 2.42. All right, so this one is going to be a 2.42, and standard deviations I already wrote for us down here. Okay, all right, so we've got our 2 expected values right there. So then the next question says, so we did what's the average value of X, what's the average value of Y? What about if we were going to add the people from a randomly chosen one from town A and a randomly chosen family from town B, and we add up the members in their house when we check? Okay, so that's X plus Y. So if I want to do X plus Y, I'm going to add those 2 together, right? Because it's just mean, so I just do the math to it. So the expected value of X plus Y is just going to be 2.92 plus 2.42, which is going to be 5.34, I hope. Yep, okay. And then what if we wanted to do X minus Y? Well, again, because it's mean, I just do whatever it says. So X minus Y is going to be 2.92 minus 2.42, which is 0.50. Okay. So the average number of people in the 2 households, if I add them together as a total, it's 5.34. And if I was talking about how many more people do I expect from town A than town B, on average, it's a half of a person on average. Okay, so that's what that means. All right, so now let's go down and do the standard deviation stuff. So remember we said means are easy, you just do whatever the math is. It's the standard deviations that are harder. Okay, So standard deviation of X and Y. So we're going to go to variance first. All right, so we're going to go variance of X is going to be 0.891 squared. And variance of Y is going to be 0.961 squared. So anytime we want to do any math to these, we're always going to go back to variance first, right? All right, so next one, I want to find the variance of X plus Y. So the variance of X plus Y is going to be 891 squared plus 0.961 squared. Okay, and I'm going to go grab my calculator and figure out what that is. Okay, I've got 0.93146, but they didn't ask me for variance, they asked me for standard deviation. So to get back down to standard deviation of X plus Y, I have to take the square root of that answer of 0.93146, and that is going to be 0.965. Okay, so notice it's not as much as just adding the two standard deviations together. Right? That would have been a 0.89 and a 0.96. Okay, it's a little bit less than that. All right, so then we go on and we're going to do the other version, which is the subtraction, right? So if I want to find out what the variance is of X minus Y, I'm going to start out with 0.891 squared and 0.961 squared, and I'm going to add. Not subtract, add. All variances always get added together, never subtract. So it looks identical. It's the exact same problem that we just did, 0.93146. The standard deviation of X minus Y is also going to be 0.965. Okay, so variances always get added together. They never get subtracted apart. So same deal with standard deviation. You don't do math on standard deviation. You do the math on the variance and then follow it to standard deviation. Okay. All right, let's do another example. So here's a probability model of winning either $100 or losing $100, where X is the amount of winnings in one round of a game. All right, so what we can see is that these are not equally likely. It looks like I am more likely to lose some money than to make some money. And that is the very first question that they ask. What is my expected winnings in one game, right? So let's go and figure that out. So the expected value of X, also known as mu sub X, right, just the average, would be 100 times 0.49 plus negative 100 times 0.51. And again, I can put these into my calculator as list 1 and list 2 and then let it calculate it. This doesn't seem that difficult to me. This is $49 minus $51. So it looks like my average is every time I play this game, on average, I'm going to lose $2. What's the standard deviation of these winnings? Okay, so here's where it would have been better if I would have just gone and put this into my calculator, but just as a quick reminder, just so that you know it, let's go do this one the hard way as well. Okay, so if I want to find the standard deviation of X, it's always whatever the X is. So my first one was a positive 100 minus whatever the average or expected value is. So that's minus a negative 2. That's going to turn into a plus 2. Okay, and then I square that and I weight it according to the probability. So this one only gets 49%. Then I do the same thing with the other one, which is negative 100 minus a negative 2 squared, and that's going to get multiplied by 51%. And then those are the variances, right? And then I'm going to take the square root of the whole thing. Okay, so this one is going to turn out into, I think I wrote this down somewhere, let me check. I think it turns out into 9996, which is $99.98. That kind of makes sense though, right? Because if on average I'm going to lose $2, but I might be up 100 or down 100, that's where my 100 is coming from. So on average, if I'm right near 0, I'm going to make almost 100 or lose almost 100 as my spread. Okay. All right. The next part says calculate the expected winnings of 2 games with random variable X. So we're going to play this game twice. So it's not an X and a Y, it's an X and another X. Okay. So if I'm going to play 2 games, what is that going to look like? So let's go and take a look at that one. All right, so on this one, this is going to be two x's, right? So I'm going to do an x plus another x, okay? So the expected winnings is going to be expected winnings of x plus another expected winnings of x, right? Means we just add together. So if my first one was -2, I'm going to add another -2 to it, and now it looks like I am going to lose -$4 on average if I play this game twice. Totally seems reasonable. All right, next one, let's go do our standard deviation. So I'm going to go back to variance. So we're going to go back to variance of x plus x. So now I'm going to take that same variance that we had before. That was this one right here. That was the variance, the 9996. And I'm going to add another 9996 together. Remember, so these are adding variances together. Okay, and then once I do that, I'm going to find the standard deviation of that by taking the square root. So this is standard deviation of x plus x. Okay, so if I add those together, I think I get, so it's going to be 9996 plus 9996, which after I take a square root is about $141.39. Notice it didn't turn into almost $200 plus or minus, right? Because each one's going to overlap a little bit when they have their own spread. So it's not quite as much as 2 to one way and 2 to the other way on average. The average spread is going to have a little bit of an overlap. So it's 141.39. Okay, so back to do not add together standard deviations. You will get it wrong if you do. All right, last question says, how will the winnings and standard deviation change if I calculate 2 times x instead of x times x plus x? So how is it different if I bring in a constant versus if I use 2 random variables? That's what they're asking us in this one to do. Okay, so on this one, they're asking us instead of x plus x, they're asking us to do 2x, right? Just 2 times the random variable. So if I want to find the expected value of 2x, I just do whatever they say. So that would be 2 times -$2, which would be -4. So from that standpoint, the average seems the same. So let's say instead of, whatever I put down to play the first one, I put down twice as much, I'm still going to end up in the same spot. Okay, so -4 would be my average if I just doubled the first set of winnings. All right, so what about standard deviation? Well, we know we have to go back to variance, right? Or do we for standard deviation? Do you remember what we did? Let's go back and look. Put it on here somewhere. Yes, here we go. So standard deviation, if we're multiplying it by a constant, it is totally fine to just do the math to the standard deviation, right? It's only if I have extra stuff that I have to worry about it, right? So if I'm doing it times, just do the math on the means, right? We're okay there, okay? So let's go and see what happens if we do times 2, right? Because we said the spread would get bigger times 2 as well. All right, so then we would do the standard deviation of 2x would just be 2 times 99.98. Okay, so that is going to turn into $199.96. Okay, so are they the same? Well, the average is the same. Either way, whether I play the game twice or whether I just double the chart of winnings and losings, losses, right? I'm going to have -4 by the time I've played the game twice or whether I double the first game. But my standard deviation is going to be significantly different. If I play the game twice, I'm going to get a little bit of that overlap of the standard deviation. And it's not going to be as much spread out as if I just double the first spread. If I double the first spread, if I was up almost 100, I'm now up almost 200. If I was down, now I'm down times 2 times as much. So if I'm given the choice between playing the game twice or just doubling the table, the probability table, I'm going to get the same average, but this one is going to be a little bit safer in that it's going to have a lower standard deviation than if I just double it. So this second one is much riskier. So when we apply this to things like gambling, right? The more you put down on the table, the bigger your risk is for reward and for loss. But if you just keep playing the game at smaller amounts, your standard deviation is a little bit smaller. So the spread isn't such extreme highs and lows. You're still going to lose $4. That doesn't change. It's just a matter of how bad is the extreme factors in how big of a switch it is to go from a loss to a win each time. All right. All right. So the last thing we have to do is do this with normal distributions, and we are done for today. So taking a look at random variables with normal distribution. So we're going to do one that's about average heights of males and females. I turned them all into decimal feet, so it's easier, so we're not doing feet and inches. Okay, so we have the average height for males is 5.8 feet with a standard deviation of 0.25. And for females, we have an average height of 5.3 with a 0.21. Okay, so they said find the expected value of M minus F. Okay, so we're basically saying on average, how much taller are men than women? So expected value of M minus F is just going to be the expected value of M minus the expected value of F. And they already told us the mean was 5.8 and 5.3. So we have 0.5 feet. So on average, a randomly selected male and a randomly selected female, the male would be 0.5 feet taller than the average female. If I were to do this many, many, many times, right, select a random male and a random female, the differences in their height should be about 0.5, where males are taller. Okay? What about the standard deviation? So that's where we have to be a little bit more careful. We're doing two variables. So if I want to do the standard deviation, I'm first going to go to variances, right? So the variance of the males, it said was 0.25, and I'm going to square that to get to variance. And the variance of the females was 0.21, and I'm going to square that to get to variance for the females. And then if I want to find the standard deviation, I'm going to start by adding the variances together. So we're going to have 0.25 squared plus 0.21 squared, and then we're going to take the square root to get the standard deviation. Okay, so putting that together, we should have about 0.326 feet. So on average, if we pick a random male and a random female and subtract their heights, we're going to be at about 0.5, give or take about 0.326 feet. Okay, that's how we interpret that value. So on average, the normal spread or the average spread from the mean difference of 0.5 feet is 0.326 feet. Okay, and that would be the average distance between the male and the female height. All right, last one. What's the probability that a randomly selected male and a randomly selected female have a difference of more than 1 feet? So here's what we do. We're going to go get whatever we need in a random variable. In this case, it's M minus F. And we're going to draw a normal curve based on that, because if the males were normally distributed and the females were normally distributed, then we're good on them both being normally distributed together, whether we add or subtract them. Okay, so let's go and draw that really quick because we've been going a long time now. I'm sorry about that. Okay, so we're doing this one. We're saying that the average between them was 0.5, that the average spread was 0.326 feet. Right, so over here would be something like 0.826, and over here, right, and they're asking basically at 1, how many would be taller? So we're looking for this part in here. Okay, now that is not at a regular standard deviation mark, so I'm going to have to go back to that calculator stuff about normal CDF again, right? So I want to go and calculate its z-score. So the z-score of M minus F is going to be, I'm at 1. The average was 0.5. My standard deviation was 3.326. So this is going to be 0.5 over 0.326, which is a z-score of about 1.5337. So I'm going to go and do norm CDF, and I want to go upwards. So my lowest number is the 1.5337. So now I need the largest number known to man. So I'm going to do 10 to the 10th with a middle of 0 and a spread of 1 on my calculator and see what I get. Okay, and I'm not going to switch just to save some time. You can go back and look at the directions from the last one. Okay, and they say this is 0.0625 or approximately 6.25%. Okay, so the probability of us finding a difference in the males being taller than the females by more than a foot would only happen about 6% of the time if we were to randomly select a male and a female many, many, many times. All right, that is it for 6.2.